The basic geospatial data models that we use in a GIS are vector, raster, and triangulated data. And up to this point, both in Introduction to GIS and in Intermediate GIS, we focused on vector and raster data representations. Vector data is focused on modeling discrete features with precise shapes and boundaries. Raster data is focused on modeling continuous phenomena and images of the Earth. Now we're going to talk about triangulated data, which is focused on an efficient representation of a surface where the Z values can represent elevation, quantity, or concentration. And if you look at the thumbnails in all three data types, they represent the same spatial extent, location, and geographic phenomena on the Earth, but they're represented in three different ways as vector, raster, and triangulated. And not one is necessarily better or worse than the other. It just really depends on what you're trying to accomplish, which data model you select. Now, if you recall, vector data is structured on points, in which points are the primitive geometry on which points, lines, and polygons are created. Raster data is structured on cells. Cells are the primitives that are arranged in rows and columns to make a continuous raster data set. Triangulated data is structured on triangles. Triangles are the primitives. Actually, technically, it's the points that make up the triangles because they store the horizontal and vertical coordinates. And so each 3 points are connected by 3 lines that make up a triangle, or what we call a face. And if you look at the image on your right, you can see I have that same X, Y, and Z axis, but this time I'm representing the triangle or the primitive of triangulated data. And so the X, Y, and Z is stored in the 3 nodes of the triangle, and then they are connected by lines that together make the triangle or the face that is plotted in 3 dimensions. Now, these triangles are arranged in a continuous and irregular network of triangles. The triangulated structure actually has some of the properties of both vector and raster data. Vector data, because the triangles represent a discrete location on the Earth, and raster, because they are arranged in a continuous network of triangles. But where it's different is they are irregular. And if you look at the example in the upper right-hand corner, you can see I have an irregular network of triangles. The triangles are continuous and their boundaries are contiguous, but the triangles themselves are all different sizes. And so why would we want to utilize an irregular network of triangles to represent elevation data? Well, if you think about the state of Colorado, there's a lot of varied terrain. If you go west of Denver, there are extreme elevations that dip into low valleys. And if you go east of Denver, it's very flat. And if we use a raster data set to represent the terrain of Colorado, if we use really small cells, we can catch all the variation that is west of Denver in the mountains, but then we're also utilizing a lot of unnecessary detail to represent the flat area that is east of Denver. If we use really large cells, we can more efficiently represent the elevations in the flat areas east of Denver, but we kind of generalize the varied elevation that we would find in the mountains. So a triangulated structure with its irregular network of triangles allows us to more efficiently represent variations in terrain. So again, if we go back to Colorado, I can use a bunch of small triangles to represent the varied and extreme elevations that occur in the mountains west of Denver, and I can use really large triangles to represent the flat areas east of Denver where there's not a lot of change in the elevation. Now, triangulated structure also includes mass points, break lines, and polygons. So it's not just the triangles, there are the points that we often use to construct the triangles. And if you look at the triangulated data representation diagram in the upper right-hand corner, you can see that I have my triangles, and where they all come together, that's where the mass points are located. But I've also introduced a break line and a polygon. The break line is the stream, which is a line vector that's introduced in the model, and it actually shapes the way the triangles are formed. Notice how they all butt up against the stream on that hard break line. We can also introduce polygons into the model. In this case, I've used a polygon as a replacement of the triangles where the lake is located. Now, a unique thing about the triangulated structure is that it always includes these 3 attributes: elevation, aspect, and slope. And that's because we most often use triangulated data to represent terrain. And so if you actually click on a face in GIS, it will always show you the elevation, aspect, and slope. In the diagram on the right with the X, Y, and Z axis, if I click on that location, it shows me the elevation is 1,254 feet, the slope is 22 degrees, and the aspect is 168 degrees. Now, if I click somewhere else on that face, the aspect and slope doesn't change, but the elevation will because it's constantly being interpolated based on its proximity to the 3 points and their X, Y, and Z values that make up the triangle. Now, we just discussed how variations in surface are more efficiently represented by an irregular network. But how do you create that network? Triangles are created from a set of mass points with elevation values, and the source data used to create those mass points might be LiDAR, survey points, contour vertices, any point data set that can provide elevation. And the process joins those points as nodes in a triangle to create the irregular network. Now, if you are using a LiDAR point cloud to generate your triangles, you might find that there's really too many points and it creates too many small triangles. And so you can use a process called Delaunay triangulation that creates a more efficient irregular triangular network. Delaunay triangulation specifies that a circle drawn through 3 nodes of any triangle contains no other point. And so when creating the irregular network, the computer iterates through different sets of 3 points, and it draws a circle through those 3 points. And if any points fall inside that circle, then it doesn't draw a triangle. But if no points fall inside that circle, then it will draw a triangle. In the example in the lower right-hand corner, the computer has drawn a circle through D, G, and E. And notice that C and F fall outside of the circle. And so in this case, the computer will draw a triangle between D, G, and E. And it will continue to iterate through all of the points until it draws the most efficient irregular network possible. Now, the faces in a triangulated structure can be symbolized by structure or attribute. And if you look in the lower left-hand corner, I'm only symbolizing the mass points. In the upper left-hand corner, it's only the faces by elevation. In the upper right-hand corner, it's only the triangle vectors. And in the lower right-hand corner, it's a combination of the points, faces, and lines. We can also symbolize triangulated data by attribute. And I mentioned previously that all triangulated data has elevation, slope, and aspect attribute, and it's very easy to symbolize your triangulated data set using these attributes. The face geometry is constructed from and stored as a collection of mass points and surface features. Mass points, again, are the elevation points that are utilized to construct the nodes of the triangles. Break lines are line vectors that are used to shape the construction of the irregular network of triangles. In this example right here, I'm using streams as hard break lines to represent drainage in my irregular network. Polygons can be used as replacement polygons or erase polygons. Replacement polygons actually replace the triangles with the polygon. And in this example, it happens to be a lake. If you didn't have it, you'd have these kind of long, weird triangles going across your lake surface. Sometimes we also use erase polygons. So for example, if I wanted to project what a mine or a landfill might look like, I might create an erase polygon that erases out that portion of the mine or the landfill, and then introduce additional points or a model that represents my future mine or landfill. Lastly, we often use clip polygons. And we use clip polygons because if you look at the unclipped tin on the left, it includes right around the edge these kind of smeared looking triangles. And so we use clip polygons that are always kind of within the boundaries or the extent of the mass points so that we get a real clean edge on our triangulated irregular network data set. And so you use these surface features and identify their role when you're constructing a triangulated irregular network. When incorporating some of these surface features into your triangulated irregular network, you can specify whether it's a hard or a soft feature, for example, a break line. And you can see the example in the image below between what it would be like if it's qualified as a soft feature, in which you have blended edges, or a hard feature, which the upper right-hand corner of the pyramid is a hard break line. And so there's a distinct difference in the elevation when you cross over that break line. So you want to use hard edges for things like streams, for example, or maybe you have a ridge line. But if you have a gently sloping hill, maybe you want to introduce your break line as a soft feature. Attributes in the triangulated structure are associated directly with the faces. There's no attribute table. And so, as previously discussed, all triangle faces include elevation, slope, and aspect. And the elevation is interpolated between the triangle points. So, wherever you click on that face, it'll calculate what the elevation is. But you can use fill polygons to assign other types of attributes to the triangle faces. Now, that attribute must be an integer, and those fill polygons will affect how the triangles are structured. If you look at the example on the right, on the top, I have a typical triangulated irregular network that's symbolized by elevation, which is really easy to do. Below that, I've used fill polygons to attribute the triangulated irregular network based on 3 different vegetative zones in my terrain. Now, I will say that it's very easy to work with elevation, slope, and aspect attributes in a triangulated network. It's much more difficult to add your custom attributes to the triangle faces. Now, in ArcGIS, a triangulated data set is stored in a geodatabase feature dataset as a terrain. And a terrain can use multi-resolutional data storage to improve performance. If you look at the example on the right, you can see how these pyramids work. And you can imagine it's a lot like when I look in Google Maps at imagery. If I'm zoomed all the way out to the world, it kind of shows the world in low resolution. And then as I zoom in, I get different levels till I get all the way down to the street level. And it shows the higher resolution data. Well, pyramids in the triangulated structure allow you to replicate that. You can see when I'm zoomed all the way out, I've got really low resolution or large triangles. And then as I zoom in, I get more and finer resolution triangles. Now, there's 2 approaches to creating pyramids in the triangulated structure, z-tolerance and window size. For z-tolerance, it's created using a vertical limit in the z-value to define the different zoom levels. In window size, it's created via a window scale system to define the different zoom levels. If you look at the bottom, you can see that is a window size type approach to creating pyramids, in which at full resolution, it draws all of the elevation mass points that are used to construct the triangulated irregular network. And then as you zoom out pyramid level 1 and pyramid level 2, it decimates the elevation mass points to have fewer and fewer points on which you construct the triangles. When you get out to pyramid 3, you're constructing really large triangles to define that particular space. And so what are the advantages and disadvantages of the triangulated data model? The advantages are it's really great at modeling variations in terrain, more triangles for variable surfaces and fewer triangles for consistent surfaces. It's really great at representing roads, rivers, lakes, etc., with surface features directly in your triangulated irregular network. It displays well at multiple zoom levels. It doesn't pixelate like raster data does. It's best for covering a small area in detail, and it has a really crisp display quality. Now, the disadvantages of the triangulated data model, it looks triangulated. It doesn't look natural always. The attributes besides elevation, slope, and aspect can be really difficult to work with. Triangulated irregular networks or TINs cannot be stored in a geodatabase, but you can store a terrain, which is a triangulated data model in a geodatabase, and I'll talk more about that on the next slide. And last, if you use your triangulated data model to create contours, they'll come out jagged. And so you want to use a raster digital elevation model or DEM to create smooth cartographic contours. In ArcGIS, there are 2 file formats that we use to store triangulated data: a triangulated irregular network or TIN, or an ESRI geodatabase or terrain that can be stored in a file geodatabase. Now, there are advantages and disadvantages to both file formats. A TIN cannot be stored in a geodatabase. So if you want to store all of your project data in a single geodatabase, then you wouldn't use a TIN to represent your elevation. You might use a terrain. Now, terrain can be stored in a geodatabase, and it must be stored in a geodatabase feature dataset. A TIN cannot use pyramids. And so the resolution, whether you're zoomed all the way out or zoomed all the way in, it's going to draw every triangle on your screen. And if you have a very large extent that's high resolution, it's going to take a long time to draw all those triangles. In a terrain, you have the option to enable multi-resolution terrain pyramids so that you can speed up both your visualization of your triangulated network, but also any analysis or processing that you're doing. Once you create a tin, you cannot edit the source features. You would have to recreate the tin from scratch. In a terrain, you can edit the source features and it will reconfigure your triangulated network. A tin, especially a high resolution large tin, has a lot slower performance than a terrain, which uses multi-resolution terrain pyramids and has a lot faster performance. A tin is a very common format, not just used by GIS professionals, but used by surveyors and civil engineers. And so it's a very easy way to move data through an entire workflow that's moving from different platforms. A terrain is a much less common format. And matter of fact, some of the geodatabase tools in ArcGIS will only use a tin and won't use a terrain. So a tin is really good for full support for 3D geoprocessing. A terrain sometimes has limited support for 3D geoprocessing. And so last, how do you create a triangulated data model? We need to set the output name and the location. And for tins, it needs to be in a folder, and terrains need to be in a geodatabase featured data set. You set the horizontal and the vertical coordinate systems. You need to select the input features, the height, if any, and the type or role it will play in creating the triangulated data model. So for example, LiDAR data for mass points, streams for hard or soft break lines, or maybe lakes or a project extent for hard or soft replace, erase, or clip polygons. You need to select any additional settings, including constrained Delaunay for efficient triangle creation, pyramids for multi-resolutional terrains. And then if you're going to create a triangulated data set in ArcGIS, you need to have the 3D Analyst extension enabled to run a tool like the Create 10 geoprocessing tool that you see on the right.